Now let's learn about kinetic energy. Energy of an object due to its motion. To start, I will introduce work-kinetic energy theorem. I have a car acted by a net force of F. This is not the forward force, but it's the net force in charge of accelerating the car. And the car accelerates along a journey of the length x. And let's say the force is constant. Anyway, I can suppose that the car starts at a velocity of v1. At the end of the journey, it ends at a velocity of v2. According to definition of work is defined as the force times displacement times cosine of theta, the angle between the displacement and the force. As the displacement and force have the same direction, it's gonna be 1 because cosine of 0 is 1. So let's define the work done by the net force to be Fx. Using Newton's second law of motion, F is ma, m is the mass of the car, a is acceleration. And then I can rearrange the equation like this. Let's put a half here and another 2 here, so they are cancelled, and we have again same expression, max. But the reason for that is making a 2ax inside the parentheses. You remember in kinematics we had an equation called time-independent equation. Final velocity or final speed square minus initial speed square is going to be 2a delta x or x. So instead of 2ax, here I can have v square minus v naught square, or final v square minus initial v square. Let's do it like that. Now I can separate them, and actually I distribute a half of m to the parentheses. Here I have a half of mv square and a half of mv square. It's a very interesting expression. Here you can define it as kinetic energy, a half of mv square, final kinetic energy, and a half of v1 square, initial kinetic energy. So kinetic energy is defined as a half of mv square. Actually, if w is addition or subtraction of two terms, both must have the same unit as the work. So if the unit of work is joule, kinetic energy accordingly will have the same unit in SI, joules. More than that, the work-kinetic energy theorem tells us that the work done by the net force is the change in kinetic energy of an object. So work done by the net force is going to be the net force multiplied by x, which is change in kinetic energy of the object. In short, kinetic energy is the energy of an object because of its motion. Objects gain kinetic energy when their speed increases. You see that kinetic energy is sensitive to speed, not the velocity. Direction doesn't matter here if the object is moving at the direction of south, west, north, east, whatever. Basically, if the speed is the same, let's say the speed is 10 meters per second, you will have the same kinetic energy for the object. So direction won't make any change in kinetic energy. So this is why we say when they gain a speed, not when they gain velocity. Another form of the kinetic energy is when you make a small change on that. Let's multiply upstairs and downstairs by a constant like mass. Okay? Consider the constant mass for the object. Upstairs I have m square v square, downstairs m. You remember momentum of the object was m times v, mass times velocity, and the magnitude of momentum is mass times speed. So here in upstairs I have momentum square. So momentum square divided by 2m is another alternative for kinetic energy. Keep in mind, kinetic energy in SI units will have the unit of joule. A vehicle is being designed to capture the world land speed record. It has a maximum design speed of 1700 km per hour and a fully fueled mass of 7800 kg. Calculate the maximum kinetic energy of the vehicle. Okay, here I have kinetic energy to be a half of mv square. Here I need the speed in SI units. Fortunately, it's not SI units, so let's write it like that. and you can divide it by 3.6 to get 470 meter per second. Now I will plug in the values, 700 for the mass and 470 for the speed. Finally, I will have 8.6 10 to 8 joules, the kinetic energy of the car in maximum speed. A car of mass 1.3 10 to 3 kilogram accelerates from a speed of 12 meter per second to a speed of 20 meter per second. Calculate the change in kinetic energy. Change in kinetic energy, delta EK, is a half of mv2 square minus a half of mv1 square. So I can write it like a half of m times final v square minus initial v square. Okay, let's do it and then plug in the values. 1.3 10 to 3 is for the mass, final speed, initial speed. So you will have 1.7 10 to 5 joules. Total work done by the net force also is 1.7 10 to 5. According to Work-Kinetic Energy theorem, the work done by the net force is changing kinetic energy. So the question could be like, calculate the work done by the net force instead of changing kinetic energy. They are the same. An object of mass 0.8 kilogram moving in a straight line has an initial kinetic energy of 24 joules. Calculate the initial speed of the object. Okay, I have initial kinetic energy, I have the mass, so the only thing remains is the initial speed. It's very easy. Let's use the main formula, half of mv squared, plug in the values, 24 for the kinetic energy, and this is the mass, and v is gonna be 7.7 meter per second. Part B, the distance in which the object will come to rest when a net force of this opposes the motion. It's very interesting. Let's say the object is a car, okay, and it's moving at an initial speed of v1. It will stop somewhere. Let's say final speed is 0. It comes to stop due to the opposing force of F. So let's say the net force acting on the car during its deceleration is F. Okay, it's 4 Newton. So we are gonna find the distance traveled by the car. Here I can easily use the Work-Kinetic Energy theorem. The work done by the net force, which is also the change in kinetic energy, is the net force times the distance traveled, Fx. You know that. So here, instead of W, I can substitute delta EK. Keep in mind that the car starts from an initial kinetic energy of this, 24. So EK1 is 24 joules, and it stops. When it stops, the final kinetic energy is 0. So change in kinetic energy, magnitude of that change, is 24 minus 0. So it's 24 easily, okay? Because it comes to stop. The opposing force is F, given as 4. X is the distance traveled. So it's gonna be 6 meters. Thank you for watching this video. Thank you for being with me. Take care. See you.